My name's Matt. This is also Matt. We both work for Stack HPC. And this talks about performance benchmarking. So how do we make sure? So we do a lot of HPC and AI workloads in Kubernetes and also in OpenStack. So we want to know, we want to be able to quantify these things. So we built a thing. So I just want to give a little bit of an overview about Stack HPC because it's important context for why we built the thing. So we're a cloud and HPC consultancy. We're about 7 years old, about 30 people based in Bristol. And our founders and most of our staff come from an HPC or science background. And we apply this expertise, but to cloud-native workloads now increasingly. So to address the modern challenges and dynamism and the explosion of tooling in HPC and AI. So we have an open modus operandi. So if you saw the keynotes earlier, John talked about the 4 opens. He's also from Stack HPC. We utilize Loki, this Linux OpenStack and Kubernetes infrastructure. We're active upstream contributors in those projects. And we engage with the scientific working groups in various mostly with OpenInfra, but also with the CNCF as well. And mostly what we do is about getting the maximum value out of your investments. And by that I mean your investment in hardware, if you run on-prem hardware, your investment in people, and your investment in software. So the way we do that is we use OpenStack and Kubernetes to provide this shared, reconfigurable, but still isolated infrastructure layer. So we have APIs we can use to manipulate our infrastructure. We then make that performant, and then we provide self-service applications on top of that to try and make this thing easy to use for scientists, in particular for our use cases. So this is obviously the bit we're focusing on today. Red arrows are clearly awesome and very high performance. So yeah, why do we want to benchmark the performance? So firstly, if I'm an infrastructure provider, I want to know, does my hardware work? Thing number one. Is my hardware performing like the vendor told me it would? Sometimes not. I might want to know if I'm running OpenStack or other virtualization. I might want to know what's the impact of that virtualization on performance. For Kubernetes, I might want to know what's the impact of containerization. I want to be able to spot misconfigurations in my infrastructure that are affecting my performance. And the flip side of that is if I see something that's not performing how I would like, are there optimisations that I can do, like hardware offloads? And on the other side of the coin, we have application developers, and they are also they should also be interested in benchmarking the systems that they're running on, because their goal is to maximize the amount of useful work that their application is doing. So what they want to know is the infrastructure working? What performance can I expect to get out of the infrastructure? If that's not what the infrastructure provider's telling me that I can get, what am I doing wrong, or are they doing something wrong? And that gives me places where I can go to my application to profile and optimize potentially, or I can go and complain to the infrastructure provider. So we built a thing to do performance testing in Kubernetes. It's called kube-perftest. And what this is it's a Kubernetes operator. It provides a framework for defining and executing performance benchmarks on Kubernetes clusters. You define these benchmarks using CRDs that are provided by the operator. We've built on top of the Volcano batch scheduler, which is a CNCF project. And we also support unusual networks using the Multis CNI project. So we'll talk more about that later. And we've implemented a handful of benchmarks so far, a combination of synthetic and reference workload benchmarks. And we've also implemented a benchmark set CRD, which basically allows you to iterate over permutations of properties of your benchmark and also to repeat those benchmarks easily. And what this does is allow us to do benchmarking as code. So what we can do is we can define a suite of benchmarks in YAML using benchmark sets and the CRDs provided by this operator. We can put that in version control. Whenever we deploy a cluster, we can run those benchmarks, and we know that they're going to be the same as what we ran before. So there's kind of three areas which we currently have benchmarks for. The first one is networking. So this is obviously quite important for a lot of HPC workloads. So, what's the bandwidth can I expect between two pods? If I've put performance tunings in, did they make any difference? Or was I just wasting my time? Is it worth buying expensive network cards with hardware offload? Quite often, utilizing the hardware offloads properly means relaxing your network security slightly. Is the trade-off worth it? You need numbers to be able to make these decisions, and this is what we're trying to do. So we support iperf. So this is a tool that tests TCP network performance between two endpoints. And we can run that on the CNI, on the host network, or on one of these special Multis networks. We support testing remote direct memory access, so RDMA, between two pods. That will also be discussed more later. And we also support MPI PingPong. So this tests MPI bandwidth and latency between two endpoints for different transports. So MPI stands for Message Passing Interface. It's used a lot in HPC to pass data around between cooperating processes. So networking's my thing, but this is the storage guy.
I wouldn't say I'm necessarily the storage guy, but I'm talking about storage today. So so this is the second of the sort of three areas that kube-perftest can benchmark for you. So really, we want to ask the questions or answer the questions: is paying for the fast storage class that in your Kubernetes cluster worth it? If you scale up your client processes of your file system, do you begin to bottleneck your I/O operations? And to do this, we use the flexible I/O tester, or FIO, which is a bit of a Swiss Army knife of testing file systems. And the way that we implement this in kube-perftest is you specify a PVC template, which makes it kind of storage implementation agnostic. As long as Kubernetes can address your storage, you can test it with kube-perftest. And we do this in a couple of modes. So you've got the read-write-once type storage classes where you get a PV per client pod. And then you also have a read-write-many type mode where you have a single PV shared by all of your client pods, which brings in a whole bunch more interesting kind of file system consistency and locking type behaviors which you can examine. And the idea is that you can specify an I/O pattern that matches your workload, whether it be read or write heavy, or random or sequential I/O, any combination of those. And then you can scale your Kubernetes pods to look at the effect of scaling on your file system performance. Then those are the sort of synthetic benchmarks. We have a couple of representative workload type benchmarks. So we have OpenFOAM, which is a computational fluid dynamics software where you run OpenFOAM across which uses MPI. You run OpenFOAM across a bunch of pods, and you can look at the wall time to make some assessment of how performant your cluster is. And then we also have some benchmarks for GPUs based on the PyTorch micro benchmarks, which allow us to establish whether our GPUs are working as we intend them to be. Currently, we have the AlexNet and ResNet image classification models set up. We have the Llama large language model as well. But there's a whole bunch more in the upstream PyTorch repository that we could add in the future. So on that note, adding new benchmarks to kube-perftest is we tried to make it as simple as possible in the sense that you have to add a few things and a container or an image to provide your benchmark tools. So essentially, it's just adding a model that defines the spec and the status for your benchmark. As I said, creating a container, making a template for the Volcano job, which describes how your benchmark works. And we have several macros for common tasks in that Volcano job. So this is adding labels to pods and doing discovery of IP addresses between pods and spreading your pods across your cluster and that sort of thing. And then finally, just implementing the pod modified and summarize methods, which these are things that basically update the status of your, or add the status of your benchmark to your Kubernetes objects, and then finally create a summary of the data at the end. So we've done a couple of real-world tests of this to sort of show you how it works. We've done these on a couple of different systems. So these are kindly provided by our friends at the University of Cambridge and GraphCore. We've kind of split these into two different setups. So particularly the GraphCore system is pretty good on the old. It has lots of fast network basically. So we use that for the networking tests. And the University of Cambridge were kind enough to donate us some A100s to do the PyTorch testing. And they have some nice storage classes. So they have a spinning disk storage class, and they have an NVMe storage class as well, which allowed us to sort of differentiate some of the storage testing. There we go. Somebody else likes storage. Yeah, we deployed Kubernetes on these pieces of infrastructure using Cluster API, which is our sort of favored method for deploying Kubernetes. Each Kubernetes cluster had a control plane, 2 worker nodes, all VMs on OpenStack, and was using the Calico CNI underneath, with the out-of-the-box tunings, just so that we don't offend any of the Tigera people. So yeah, thanks to all of the people that provided infrastructure for this. So talk a little bit about storage. As I said, we benchmarked this on Cambridge. This YAML file sort of describes, or this YAML describes what a benchmark looks like. It's quite slimmed down. FIO has a lot of options that we can address in the YAML file, or in the YAML, but this is as simple as I can make it to fit it on the slide. And we created one of these per storage class. So we've got the spinning disk, we've got the NVMe, and we also benchmarked the local disk of the Kubernetes nodes just for fun, really. We wanted to test bandwidth as much as we possibly could, so we're doing nice large IOs here, so 4 megabyte IOs. And then at the bottom, you can see this permutations and product configuration. Essentially, this describes each benchmark is the product of those 2 lists. So we'll be running with 2, 4, 8 workers in read mode and write mode to generate the complete benchmark sets. So as I said, the sort of idea is to scale clients, measure the read-write performance of each of the available storage backends to examine whether paying for the NVMe storage is actually worth it for my workload. So this is what the data look like. I guess first thing to say is, well, in fact, the spinning disk storage is in red, the NVMe storage in blue, and the local disk is in green. First thing to say is that we can achieve much higher bandwidth using the networked block storage, which is kind of interesting. We didn't measure latency here, but we'd expect the latency to be much lower on the local storage. So if your workload is latency sensitive, that would be an interesting point. We did see that we topped out our read and write performance at around 5 gigabytes per second, and that didn't appear to be related to the storage medium. So the spinning disk went as fast as the NVMe. So obviously the bottleneck is somewhere else that isn't explained by the storage medium. It's probably the network. We can go and ask our friendly cloud admin to go and have a look at the network. And from a workload point of view, the interesting thing is that if your workload is strongly read-heavy, then you don't actually benefit much from having paying for the fast storage. You get about the same performance. However, if you've got a strongly write-heavy workload, then you might have to scale your clients to past the extremity of this graph to be able to get equal performance between the 2 storage backends. We also looked at the PyTorch microbenchmarks in Cambridge on their A100s. This is so the GPU support was provided on our Kubernetes clusters with the NVIDIA GPU operated device plugin. We did training and inference for ResNet 50 and AlexNet. And essentially, we just increased the input batch size each time to look at the response of the benchmark as we increased the input data size. So in this case, the y-axis is wall time, so lower is better. The CPU, we looked at basically the same test on the CPU and the GPU. Obviously, expectedly, the GPU dominates the training. It's much faster at doing any of the training benchmarks. But we did see that you can keep adding input data to the GPU, and it doesn't really seem to have much impact on how long, or certainly not. We didn't get to the point where we saturated adding input data to the GPU tests to influence the difference there. So something other than number crunching is a bottleneck. And what we did see is that pushing data onto the GPU takes quite a long time, so around 70 or so seconds. And in these particular micro benchmarks, that completely dominated the actual training part of the process. So we don't really know whether there's some hardware issue or a misconfiguration there, but there's something to investigate there.
How are we doing for time? Yeah. I'm about to delve into some networking. So.
Good luck, good luck, everyone.
Buckle down. Yeah. So I'm going to talk about some of the network optimizations that we apply with our clients, and how we assess the performance of these. So there's three kind of steps to. So hopefully you all saw John's talk earlier. You know what Loki is. We mentioned that earlier. So RDMA is remote direct memory access. And this basically allows you to, from one computer, to directly access the memory of another computer without involving the OS network stack at all. So this is supposed to be really high bandwidth, really low latency. And that's obviously good for HPC. So there's kind of four things we need to get RDMA into our Kubernetes pods. First, we need a Kubernetes cluster. That's Cluster API. I could do a whole talk on that, and I will probably in the future, and have in the past. We need something that looks like a real NIC inside our OpenStack VM. We need something that looks like a real NIC inside our Kubernetes pod. And then we need all the RDMA goodies in our Kubernetes pod. And there's some logo soup on the right-hand side. So how do we get a real NIC inside our OpenStack VM? We use SRIOV. So this is single root input-output virtualization. And what this does is it allows you to share a PCI device, like a network card, between multiple VMs using these things called virtual functions. And this allows the VMs to utilize features like hardware offload directly. As I said before, this quite often means turning off port security on your network. So use with care. Basically, if performance matters, that's when you should use this and not otherwise. So now we've got a real NIC inside our OpenStack VM. How do we get that NIC into our Kubernetes pod? So again, I could do another whole talk about Mac VLAN. But we use the Mac VLAN CNI to then enslave the SRIOV device. And what that allows us to do is split that interface into multiple interfaces, but those are directly connected to the parent interface. And they all have a unique MAC address, and this turns out to be important for RDMA. And the important thing to note is that that traffic is directly routable on the underlying VLAN without having to go through a NAT or another encapsulation. So this is important for performance. And then we use Multus to assign these virtual interfaces to the pods. So Multus gives us some CRDs to define these networks and then reference them in our pod specifications. So does it work? Let's do some benchmarks. So this is an example of an iperf benchmark running on a special Multus network. So you can see I've set the network name to default /SRIOV net. That's the namespace and name of my Maltus network, and then I use iperf to measure the TCP bandwidth between two pods. Those pods have anti-affinity rules, so they end up on different Kubernetes nodes. The Kubernetes nodes have anti-affinity rules in OpenStack so that they land on different hypervisors. So this is two pods in different Kubernetes nodes on different hypervisors. And then we run that. We ran this for the CNI for the host network, which is a VXLAN. So we have a VXLAN control network and then a high-performance workload network. And the host network, because of the way we set the Kubernetes cluster up, where the control plane nodes only live on the VXLAN, that's the host network. And then we have the SRIOV network, and we ran this for multiple different stream counts using the product that Matt described earlier. This is what we saw, so yes, makes a big difference. The CNI is worst, as you would expect, because it's double encapsulated. It's a VXLAN inside a VXLAN, so it's going to be terrible. The host network still suffers because it's still a VXLAN, but the SRIOV and MAC VLAN goes straight up. But you will notice that it's capping out at 100 gigabits per second when we have a bonded 2 by 100 gigabit interface. So there's something for us to investigate there. We're not really quite sure what's causing that right now. So, but this is why we benchmark, right? So we know to go look at that. What we want to do now is look at how we can use RDMA, and in particular RDMA over Ethernet. So RDMA is a protocol that's designed for InfiniBand networks. But there's this protocol called RoCE, which stands for RDMA over Converged Ethernet, which allows you to run this protocol on an Ethernet fabric. And then we want to, our target applications here are the MPI ones that are doing a lot of message passing, and this is a very common thing to do in HPC. And also actually, as it turns out, things like kubeflow will use the MPI operator to do quite a lot of stuff. So this is quite relevant for AI as well. As I said earlier, what this remote direct memory access allows us to do is reach out into the memory of another machine without involving the OS networking stack. So we should be able to get really low latency, really high bandwidth. We use the RDMA shared device plugin to do this in Kubernetes, so that allows us to partition the RDMA device across pods. You do have to build your applications with specialist support for this, but OpenMPI supports it as a transport via UCX, so you don't actually have to do anything special if you have an MPI application. So this is what it looks like. So we can see here that so this is message size on the x-axis and bandwidth and then latency at the bottom on the y-axis. And you can see that so this is message sizes up to around 32 meg. So you can see that with the larger messages, we're able to saturate the network with RDMA, which is quite nice. The read performance is slightly lower because that's a bidirectional thing. You have to send an ACK, and whereas the write's just a put. And you can see that in the latency as well, where it's basically half. So how does this translate into MPI performance? So we can see on the right-hand side that our MPI PingPong test we're able to get much higher bandwidth with RDMA. And also, our latencies are really, really tiny. Something like 2 microseconds, which on an Ethernet fabric is remarkable, right? And then we also wanted to look at how this translates into a real-world MPI application. So we ran the OpenFOAM benchmark, and we measured the wall time. With the CNI, it's pretty slow. With MPI in TCP mode on the SRIOV network, it's pretty good, actually, but it's still twice as good with RDMA. So this is telling you, if you've got an MPI application that's sending lots of MPI messages, you want to be using RDMA. This is important stuff for HPC, at least. So last but not least, how can you get involved? So this is all open source. So go look us up. Try it on your Kubernetes cluster. Let us know if you find any bugs, or even better, fix them. Or implement your favorite benchmarking tool. So as Matt said earlier, we've tried to make implementing new benchmarks as easy as we can. We're always open to expanding the range of benchmarks. And yeah, get in touch.